So thank you very much, especially to Yasuno and Maekawa who invited me for these lectures. So I will give a series of 4 lectures. So the title of the lectures is Blow-up, Compactness, and Partial Regularity for Partial Differential Equations. And I want to, so this is a very general topic in PDE, and I want to look at 2 particular situations. One in homogenization for the first 2 lectures, basically, and their 2 last lectures. So this afternoon will be about epsilon-regularity in fluid mechanics. So let me introduce the subject of the first lectures. About compactness methods in homogenization. So please let me know if my writing is good enough, otherwise I will try to improve it. So this lecture this morning will be based on the simple elliptic equation, divergence form, and linear, posed in a domain, let's say B0 R. And I will be interested in regularity theory for this equation. So regularity theory is the study of the local behavior of the solutions. And you will see it to some of you who are familiar with long-term behavior, study of long-term behavior of PDEs. In some aspects, it has some similarities about the methods. But of course, there are huge differences, but from a very general point of view, there are some similarities. So one aspect I would like to emphasize is that the global versus the local aspect. So you can study regularity of PDEs from a global point of view, meaning that you have a PDE, so you study an initial value problem to some PDE, and you, for example, you studied the regularity of the solution in terms of the solution being in some Sobolev space, and you can study the growth of Sobolev norms in time, etc. So in terms, for example, you can describe the regularity in terms, for example, of Fourier modes. So this is what I call the global approach. This is the approach we will not take here. The approach we take here is a completely local approach, meaning that I will work in physical space, and we will assume that we control the solution in some big ball. In some weak norm. And the goal is to control the solution in some smaller norm, but in higher, in some smaller ball, but in higher norm. So the goal will be, for example, to have an estimate on the gradient in L infinity of, let's say, B0 1/2. Which is controlled by U in L2 of B01. So a weak norm controls a stronger norm of the solution, but in some smaller ball. So this is what I call the local approach in some sense. And everything I will talk about today will be a local result like this. And another point I would like to stress is the fact that the polynomials are the building blocks of regularity theory. So you can already see that at the level of Taylor formula, for example, so when you have a function, you Taylor expand the solution around a point, and the Taylor expansion is a polynomial expansion. But at the level of PDE, what will tell you that the polynomials are the building blocks of regularity theory is some kind of Liouville theory. So all the entire solution to some PDE like this, so entire meaning solution in the whole space with some specific growth at infinity will be of a specific form, like constant or first order polynomial, etc. All right, so now I would like to underline a few recurrent topics in the lectures. So some things which will come over again and again. And so the first topic, so these are just things to have in mind when I do the lectures. So the first topic is localization. So everything we'll talk about will be local, and we'll try to localize all the time by taking test functions, etc. So this may be more or less complicated, but we will always try to localize. The second topic is multiscale. So in order to get an estimate like this, we'll compare several scales. So here, some large scale would control some quantity related to the solution in at some smaller scales. So large scales control small scales. So this is the basic thing in regularity theory. And for example, we'll have a characterization of Hölder continuity in terms of the decay of the integral, so the mean, so int bar, so this symbol will all the time denote the mean. So we'll have a characterization of Hölder continuity of U depending on how this integral grows in terms of rho. And this symbol here always stands for 1 over B0 rho. So the Bldg measure of this set times the integral over the set. All right. So another point is comparison to polynomials. So I told you the polynomials are the building blocks of regularity theory. So it's like in Taylor formula, when you have a function, you Taylor expand, and you have a remainder. So you estimate the remainder. It's like here would be the same. We'll compare the solution U to a polynomial expansion, and we'll measure the remainder in some integral norm. Okay, so this will be something we'll do all the time. Compare the function to polynomials, and the simplest polynomials we'll take will just be zero-order polynomials, typically constants. So very often we'll have our integrals, so int bar over b0 rho of u minus a. So where a is some constant. And a last point I would like to emphasize is compactness. And in particular, improvement of flatness. So the basic idea of this local regularity estimate I will show you is we'll have a limit, and we'll have some we'll take some limit, and at the limit we'll get an equation which for which the regularity properties are better. So this could be, for example, if you take regular coefficients. So let's say the A in this example is regular. So let's say Helder continuous. When you zoom in, you will converge to, so for example, you zoom in around 0. You will converge to an equation with coefficients a of 0, which is constant. Okay, so at the limit you get a constant coefficient equation, and the regularity theory for a constant coefficient equation is simpler, of course. We'll see that in a minute. And from this improved regularity at the limit, you can get something back on the original equation. So this is one of the key ideas, is that we'll take limits, and something at the limit will be better. Some regularity at the limit will be better. So this is one example I will not talk about today, but the other example is that this is when you zoom in. Another example is when you zoom out. When you zoom out, so this will be, for example, related to homogenization. When you have some, so zooming out will be equivalent to looking at, for example, highly oscillating coefficients. So when you put a 1 over epsilon here, as we'll do. And at the limit, when epsilon goes to 0, if you have some good structure assumptions on the coefficients, for example, the coefficients are periodic, if you zoom out, you will get the constant coefficient equation. And this constant coefficient equation, again, has some improved regularity. And the whole thing is how to go back to the original equation. So I write it here, ax over epsilon, if A has some structure assumption. So, of course, the simplest structure assumption we'll look at today is periodicity. But it could be quasi-periodicity, or you could take a more general framework, but we'll stick to periodicity today. And the last example where this compactness, so this improvement of flatness appears, is when you have when you take a nonlinear equation, and for some reason you know that the nonlinearity is weak. So when you take the limit, you will end up with a linear equation, and the regularity for the linear equation is simpler than that for the nonlinear equation. So you will get some improvement of flatness from the linear equation. So how do I call this? Yeah, just by improvement of flatness, just by convergence to a linear equation. So this will be the topic of this afternoon's lectures, so about epsilon-regularity. And this will be the topic of this morning, about homogenization. All right. So these ideas of improvement of flatness for regularity theory are originated in the work of Algren in '68. So about their study of the regularity of minimal surfaces. And then a lot of people used these ideas and applied it to calculus of variations. So I just said some names. Of course, the list is far from being exhaustive. So Evans, Gariepi, Giaquinta. So this is just to have some names. So this is in calculus of variations. And then these ideas from calculus of variation were further taken to the field of fluid mechanics. So for example, for this epsilon-regularity results. And today's lecture will be based, so this morning's lectures are based on a series of papers of Avellaneda and Lin. And especially two, one in '87 and one in '91. All right, so now I would like to start the real math part by introducing an inequality which is at the key of regularity theory for elliptic equation, which is the Cacciopoli inequality. So again, I will consider the equation I mentioned before. So now in the fixed domain B01 in RD. And I would assume that A is, so A is a function of X, is measurable, is elliptic, in the sense that there exists lambda, strictly positive, such that lambda psi square bounds from below A of X psi dot psi uniformly in psi.
How do you put the sign of minus? It's
okay.
It's 0, right?
Yeah. No, this is just a habit. So thank you. I will always put minus sign because I'm just used to it, but this is just okay. And so it's elliptic and it's bounded from above. So there exists L simply positive such that this holds. So yeah, you have to keep in mind that A is a matrix. A is a matrix of entries A alpha beta with alpha and beta in 1D. But it could even be, so this is an equation, and I could even consider systems. So I could even consider, so I just mentioned it here. So by the way, everything I will mention today works for this system I talk about now. But I will use the equation notation because it's simpler. But everything will work for systems. So systems would be, I have a U, which is not a scalar function, but a U of X, which is in Rn. And I have an A, which is A alpha beta, Ij with Ij in 1n. Okay, so the way to make sense of this equation is with using, so the minus divergence A gradient U is D alpha, A alpha beta of X, D beta U is equal to 0. And yeah. Okay, so here I'm using Einstein's convention about repeated indices, which I will do sometime during the convention. So when the indices are repeated, I'm just summing on them. Okay, so so now I will have a first estimate which is really crucial, which is a Kac-Chapoli inequality. So, so I will take a cutoff function. So I want something which is local. So of course I have to take a cutoff in space and in order to localize. So I will take a cutoff phi. So given R, let's say 0, rho, and R, I will take a cutoff phi, which is 1 on B0 rho. Let's take it C infinity compactly supported in B1. And the support of phi is contained in B0 R. And I want to bound on the derivative. So nabla phi in L infinity will be bounded by 2 R minus rho minus 1. So phi is really just R rho. Okay. So now I will test my equation against phi squared times u. So if I test the equation against phi squared times u, I get that 0 is equal to, so the integral over B01 of a of x gradient u, and then a gradient of u phi squared. So either the gradient hits the u or it hits the phi squared. So this is equal to B01 a of x gradient u dot gradient u phi squared plus B01 a of x gradient u dot so 2 gradient phi u times phi. So under so I can use ellipticity, so I get a of x gradient u dot gradient u. I'm sorry. The norm of u squared. No, let me keep it like this. So gradient u times phi squared. And on the right, I get so 2 times gradient u times phi squared, 1/2, times the integral over B01 of u u times gradient phi.
So you write this so that equation, the second line, is it correct? The second, the pi is already is nabla pi. So do you need to write pi?
I put the phi with the gradient u. Yeah, it's yeah. And so this term I cannot absorb in the left-hand side. So I get 1/2, and then this term is not here anymore. And then this term I can bound by gradient phi in L infinity times the integral over B0 R minus B0 rho of u squared. Okay, and eventually this is smaller than 1 over r minus rho, and I get that lambda gradient u times phi squared is smaller than is smaller than so lambda squared one over r minus rho squared b0 r minus b0 rho u squared. So let me write it like this, with some constant here which depends on L, lambda, and maybe the dimension. So here I can also remove the phi because I can bound this from below by the integral on b0 rho. So this is Kyoto inequality, and this gives you an estimate of the gradient of u on the smaller ball by an estimate of u on the bigger ball, or even better on the ring b0r minus b0 rho. And actually, I could do the same computations for not only u, but u minus xi squared. So where xi is any real number. Because xi is a solution of the equation. So I can do the same proof by getting this. And this is really the key tool of the regularity theory I will talk about. So let me show you just a nice application of this, which is the so-called Hall filling trick. So by an observation of Widman, so Widman's Hall filling trick. And so first you notice that if I have an equation with constant coefficients, what I did for u, I can always differentiate the equation, and it will work for nabla u and nabla square u, etc., etc. So I can iterate this inequality for an equation with constant coefficients. And then I will get a bounds on nabla ku for arbitrarily large k. And then I get the smoothness of my solution, because it will be in all Sobolev space. So I already get smoothness of solutions for constant coefficient equations. But here I would like to talk about equations only with measurable and bounded coefficients. So the constant here, the very important point is that it only depends on the bound, L infinity bound you have on the coefficients, and the ellipticity constant, and nothing else. Not on the regularity of the coefficients. That's the fundamental point. And so for just bounded measurable in, so I can iterate the inequality. So I can have, So if I take r is equal to 1/2 and rho is equal to, r is equal to 1 and rho is equal to 1/2. So I have that B0 1/2 of gradient u squared is bounded by a constant over so let me just check. Yes, some constant times the integral over B01 minus B0 1/2 of u squared. And from this, I can apply Poincaré's inequality. So I get that this is smaller than another. So I take the same notation for the constant. Okay, and now you recognize that this is the integral over B01 of gradient u squared minus the integral over B0 1/2 of gradient u squared. Okay, so I can put this part here on the left-hand side, and I simply get B0 1/2 of gradient u squared is smaller than c over c plus 1, the integral over B01 of gradient u squared. So I get some constant here which is strictly smaller than 1. And I can iterate. So if I iterate this trick, I end up with the integral over B01 over 2k of gradient u squared is smaller than c over c plus 1 at the power k, B01 of gradient u squared. So eventually, I can get from this inequality that for any row in 0 1/2, and if I let, so this is just simple computation, so if I let alpha be, so I just give it to you, log of c plus 1 over c over 2 log of 2, I get that the integral over B0 rho of gradient u squared is bounded by c rho to alpha times the integral over B01 of gradient u squared. So this is the key inequality, and in dimension 2, this inequality gives me that U is Hölder continuous with, so U is C0 alpha. So in dimension 2 only. So U is C0 alpha of B0 1 over 2. So this is in dimension 2 only. So we'll see why this implies Hölder continuity. And in higher dimensions, I just mentioned it. We have so D bigger than 3. We have the Bldg-Nashmoser estimates. Which also give that solutions to elliptic equation with bounded measurable coefficients are Hölder continuous with some exponent. But with more complicated methods. So in dimension bigger than 3, you have to work much more. And moreover, so U is C0 alpha, but the techniques are completely different. And moreover, this only works for equations, n equal to 1. So this is the only result which only works for equation, which I mentioned today. And there are counterexamples. Yeah, there are counterexamples for n bigger than 1 and d bigger than 3 counterexamples. To Hölder continuity. For the counterexamples, you can have a look to the book of Jack Winter. For example, multiple integrals, and or Jack Winter Martinozzi. Okay. Yeah.
The denominator, the r minus will get larger and larger. So the coefficient.
No, because if I take r and rho, so r will be 1 rho. So this is 1/2. Okay, so this is eventually it's between this step and this step. So I get 2c here. But and then I don't iterate this inequality, but I iterate this inequality. So so this is 2c if you want, and then I get 2c over 2c plus 1, and I iterate this one, and yeah. Other questions? Because I will now start talking about
If we
homogenization.
substitute C plus 1 for C plus 5 or C plus 6, is that inequality still hold? C over C plus 1 or C plus 5, C plus 10, or
Yeah.
it will still hold the inequality?
I mean, the plus 1 you get from here, from this one. So I don't think. I mean, that would change the constant capital C, and no, I don't think so. Yeah. Are there other questions? All right. So. Now I would really like to start the topic of homogenization and of improved regularity. So I will talk about C1 alpha improved regularity. So here I will consider again divergence from elliptic equations, but instead of taking non-oscillating coefficients, I will take highly oscillating coefficients. So I will put an epsilon here, gradient Q, in again the fixed domain B01. And I will take A, again measurable, elliptic with constant lambda, and bounded. and periodic. So DD periodic. So this is really the fundamental point. And I will denote this class of A by A this A of L, lambda, and per for periodic. Because I will prove result uniform for matrices uniformly in this class. So I need to get a notation for this class. And so here the topic is somehow we'll use the limit when epsilon tends to 0, for which we'll get a constant coefficient equation, so with improved regularity properties, to get regularity estimates on U epsilon uniform in epsilon. So the goal is uniform, so regularity estimates uniform in epsilon. And in the title I have improved regularity, and the improved regularity will only hold on scales, on large scales. So that means if you consider the scales from 0 to 1, and if you have 1/2 here, and epsilon here, the improved regularity will only hold for the scales from epsilon to 1/2. So these are the scales where the regularity of the solution, in some sense, is determined by the homogenized equation at the limit. Below, between 0 and epsilon, you will need some smoothness on the coefficients to have the smoothness of the solution. So I will make this more precise in the lectures later, but this is something to keep in mind. When I talk about improved regularities, it's really the regularity which I get for epsilon between, for R, for scales between the small scale epsilon and 1/2. But below, I have to use the regularity of the coefficients to get regularity of the solutions. Okay, so so before talking about regularity, I need to tell you some things about homogenization. So So homogenization is the idea that you have an equation with oscillations, and at the limit the oscillations average, and you get something, a constant coefficient equation. So one of the key objects to construct, to talk about the limit, and to construct expansions for U epsilon is what we call the corrector. So the cell corrector here in periodic homogenization, which is a function, which is a solution to the equation minus divergence A of y gradient y plus k of y is equal to 0 in RD. So, so y for me is always the blown up scale, so the fast variable x over epsilon, in some sense. And so chi is a periodic function. So that this y plus k of y is a solution of this equation in the whole space. So y of plus k of y is what I call an A harmonic function. And to have a unique chi, I also impose that the mean of chi over the terms, so TD, is 0. So in that way, I can define a unique chi which will solve this equation. And that you can easily get in periodic homogenization when the A is periodic. But if you had a more complicated structure, like quasi-periodic or even random, it's not at all clear that you could solve this equation. So here it's very easy to solve, and that's one of the crucial simplification of periodic homogenization, is that this equation is very easy to solve, and once you have the corrector, you know almost everything about the solution, at least up to order 1 in epsilon. If you have a more complicated structure, this is really one of the main topics, for example, in the developments of random homogenization in the last years was to analyze the correctors and to get bound on the growth of the corrector at infinity. But here, we easily get that the solution to this problem plus the corrector is bounded. Okay, so once you have this corrector, you can expand U epsilon. So formally, as some, you would like to expand it as some U bar of X. So U bar will solve some homogenized equation with constant coefficient plus epsilon kx over epsilon gradient U bar. So this is typically the ansatz you would expect for U epsilon. And if you look at this close to a point x naught, so this would be U bar x naught plus epsilon x minus x naught over epsilon plus chi of x over epsilon dot gradient U bar. So this is formally, but just to give you an intuition. So the thing I will do in the proofs will be to compare this solution U epsilon to this kind of polynomial. So this is constant plus polynomial with some correction. Okay. So I will call this A harmonic linear functions. And I will compare my solution to this A harmonic linear functions in order to get C1 alpha regularity. Okay, so, and U bar, as I told you, will be the solution to the homogenized equation. With constant coefficients. So the homogenized equation is minus divergence A bar gradient U bar is equal to 0. With A bar, which is given by the mean of A of Y plus some correction. And the correction is coming from the corrector. Okay, so you don't need to remember the exact formula, but just remember that the A bar is constant, and it's the mean of A plus some correction due to the special structure. And so these A-harmonic linear functions, you really see that as a linear functions plus some kind of wiggles, plus some small oscillations on the polynomial, on the linear function. So now I will prove the key lemma, which is about the convergence, the weak convergence of the U epsilon to the U bar. And this lemma will be crucial for the analysis of the theory. So the lemma is the following. So the lemma basically tells you that the solution to the original equation converge to the homogenized equation. And this is not at all trivial. For one reason I will mention right after the lemma. So I take A in A for lambda L, and epsilon k going to 0. And I assume that so UK is a family of solutions to A of x over epsilon gradient U. So it's a family of solutions to this equation. And UK is bounded in W1 of B01. So I have a bound in on UK in L2 plus its derivative in L2. Then up to a subsequence. So I can extract a subsequence. UK converges strongly in L2 to some U bar. So this is strong in L2 of B01. The gradient UK converges weakly to gradient U bar in L2 of B01. So convergence of the gradient is weak. And the last point, which is the main point of the lemma, is that AX over epsilon k, gradient UK, converges weakly to A bar gradient U bar. So again, this convergence is weak, and this is actually the main result of the lemma. So why is particularly this convergence not trivial? So this convergence is not trivial because UK is only converging weakly. AK is a periodic, highly oscillating function, so it's only also converging weakly to its mean. So I have the product of two weakly converging sequences. So it's not at all clear that the limit will be the product of the weak limit. I mean, actually it isn't. So because we know that the A bar is not only the mean of A plus, but the mean of A plus some correction. So, so the main point of the lemma is to prove this. And I could, what I actually need is a slightly more complicated version of this lemma, but I will prove it in that way, where I also have a sequence of matrices AKs. So why do I need this? Because I will prove results which are uniform in this class of matrices. So I need to get a matrix AK here, and there is an analogous version of this lemma. But the key thing to understand is about fixed A. So I guess it's 45 or something.
Yes.
Yeah, maybe we make a short break and resume.